is a molecule of life. This is a cell, and inside the nucleus are the chromosomes. Chromosomes come down and they unravel. You unravel the chromosomes, and you're looking at the DNA. And the DNA is made up of the bases. We're going to see that in a minute. And what the DNA does is the good, not the junk, the stuff that works, makes proteins. What you have to understand is about 97% of all of this, of everything in here, 97% is junk or non-coding or whatever you want to call it. It doesn't make the proteins. About 3% of this runs us. The rest of it is like, what is it there for? We're still trying to figure that out. Could be spirit, could be a number of things. But junk is not dealt with at the scientific level because it's not quantifiable. They can't quantify it. So anyway, we need to all understand this, and we're just getting started. Okay, next slide. We'll see a different look at it. What we were looking at is made up, the base pairs are only 4. There are only 4 base pairs. Thymine, adenine, guanine, and cytosine. And that's it. And these two go together, thymine, adenine, and guanine, cytosine go together, and they don't mix. It's these two, and they make these steps, the base pairs. These are the base pairs. These are the nucleotides. These are the nucleotides. These are the base pairs that the 2 nucleotides come together and make. So that term is used kind of interchangeably. When you say a nucleotide, you know, if you know the nucleotide, you know what its partner is automatically. So all you need is the nucleotide, and you know it's a base pair because you know what the other side of it is going to be. So you can strip them apart like this and get to nucleotides, and you know what goes on the other side of it. So nucleotide base pairs, don't be confused by that. It's essentially the same thing. We tend to use base pairs, but if you see nucleotides, not a problem. So you have all of this, and all 3 billion of them are wound up like a wad of rubber bands in the nucleus of the cells that we saw just a minute ago. They're just like rubber bands, just wadded up. And that's it. Very, very tightly packed. Next slide. This is early DNA testing used primers, 20 to 30 base pairs long. Below is an early array in a gel sheet. Now this is important to understand because you have to understand the story of the Starchild's early DNA testing. Next slide. The first testing was done at the University of British Columbia. I made a mistake. We couldn't, there were only 6 labs in the world that could do nuclear DNA at that time. None of them would touch the Starchild. And so there was this lab here. It was a new lab. It was a dental forensic lab, totally incapable of dealing with ancient DNA. And the guy said, well, I'll just try to find out if you have live DNA there. Because sometimes a skeleton or bones can be so degraded that they just can't recover anything, but either mitochondrial or nuclear DNA. He says, I can't recover mitochondrial, but I can recover nuclear, and if I find anything nuclear, you'll at least know it's worth trying to gather the money and keep going. So I said, okay, great, next slide. So what he came up with was after 2 times where they contaminated it, and a 3rd time, they came up with this result. Now by then, a guy on the team, one of the kids there, again, this is a university, this is a main geneticist and kids and students doing the work. And they're just screwing it up. They're just contaminating it every time. The first 2 times, and they did it again this time too. But by then, the rest of the university had heard what they were doing, that they were working on maybe an alien skull, and the other professors dropped down on them, and now they were just trying to get rid of us. Get us off the camp, get us out of the deal. So he said, after the customary number of PCR cycles, 28, there was a very weak 200 picograms gender profile from the second bone sample taken from the child's mastoid process. Now, normally 1,000 picograms were the usual minimum threshold at which you could tell anything about what you had. And the guy says, we only got 200 picograms, but we know that it's a result as an XY chromosome, which tells us 2 things: the child was male and it was human, right? This is a totally BS report and a totally BS answer. But the problem was in late 1999 that went out as the official answer. And it was exactly the answer that mainstream science wanted. Human male. End of story, end of tape. We don't have to worry about the Starchild anymore. And so to this day, you will read that this is the answer, that it was already proved to be human, even though this was in '99 when they were using primers of 20 to 30 base pairs long, and it was easy to make mistakes, and these guys didn't even get it. They didn't even get it because why do we know? The next slide. But now this, you have to understand, this caused a disaster to our team. We couldn't get a hearing anywhere. The Bowl lab report equaled 3 years of dead time. 3 years from November of '99 to November of 2002. When, by that time, I had spent so much time and energy and effort trying to resuscitate it. I had gone horribly into debt, about $50,000, and I was going to have to go bankrupt. So my girlfriend at the time says, "This is killing you. This is killing you. You have got to stop this. You've got to just give it up." So I sent out the word that I was, I just couldn't go anymore. I had done my best, but somebody else was going to have to take over and go from here. And then, next slide, Miss Belinda McKenzie raises the dead. Raises the dead. She contacted me, first contact, "What do you need?" "I don't know what I need. I haven't even given it any thought for so long. Find out what you need and let me know." And so we did, and we found out, and we told her, and well, she did her due diligence. It took a few weeks, but finally a check arrived and we were back in business. So Belinda is one of the key and major players in this whole thing. Without her, I wouldn't be here today, and that's the truth. So again. We love you, babe. We love you. All right, next slide. Now, so what she paid for was a real DNA test from real geneticists who were capable of recovering ancient DNA. Now, what do I mean by ancient DNA? Older than 50 years. That lab in Vancouver, they only dealt with fresh DNA. They couldn't deal with very old DNA, much less 900 years old. Over 50 years, there's a huge amount of degradation, and there's a huge amount of contamination from the bacteria of death that we were talking about. Right? So this is not an easy thing to do, but these guys could do it because they had worked on the Kennewick Man. Anybody heard of the Kennewick Man? The Kennewick Man. Yeah. This was a skeleton that was found in Washington State on Indian territory, and it looked clearly like a normal European. And the Indians went bazookas because they have these gambling concessions in the States, because they get all these special privileges because they're supposedly the first people to settle America, and so they work really, really hard anytime something comes up to indicate that somebody was there before they were there. And the Kennewick Man was like 9,000 years old and looked like a European, so that wasn't going to happen. So they made the Clinton administration cement the whole thing over, and the Kennewick Man, and it became this big legal case, and it took like 6 years to be able to study it. Well, these guys studied it, and what they found was that the Kennewick Man was exposed on a riverbank. That's how it was found, and the water would wash in and cover it, and then water would go out and the sun would bake it, and so it was absolutely sterile. There wasn't any nuclear DNA, there wasn't any mitochondrial DNA. There was just nothing to recover from. So at that time, later they were able, as the refinements got better, they were able to tell its date and stuff like that. But at the time, that's where they were. But these guys did a great job, and here's what they did. Next slide. Using, again, primers. Keep in mind, 20 to 30 base pairs long. 20 to 30 base pairs long, short-length base pairs. They recovered the human's mitochondrial DNA, and she was from haplogroup A, and they found mitochondrial DNA for the Starchild from haplogroup C. And that's what that means. They also found, next slide, that in 6 attempts at finding the nuclear DNA, they couldn't do it. They were 10 times, 100 times better than the lab in Canada, and they couldn't do it in 6 attempts. They could not find nuclear DNA. So that proved right here that what they had said in '99 for Vancouver was wrong, just was wrong. It should have been thrown out right there. Again, you can still read on the internet that the '99 test was better than this test. And this test has turned out to be wrong because those primers are so short, 20, 30 base pairs long, and in 3 billion base pairs, it's not too hard to find pieces 20, 30 long that match up. But when you get out to 2 and 3 and 400 and 500 long, it's a different story, as we'll see with the new geneticists. Next slide. So, but out of trace genetics, those two guys, the result was that the Starchild skull was a human-alien hybrid, and some of you might remember who have been here when I talked about it as a human-alien hybrid. You might have seen that very same slide. We believe that from their test in 203 right up until 210. We believed that was the result. Next slide. It was what the guys told me in 203. I said, well, what can we do now? And they said, well, you're going to have to wait, if you can believe this, 3 to 5 years for this new technology to come on board, that instead of primers, it's going to do it base pair by base pair by base pair. And that's what you need, because if your thing has never been seen before, the base pairs are how it has to come out. You have to be able to pull it out base pair by base pair. Sure enough, almost three years to the month. That was July 203. This is July 206. A company called 454 Life Science announces that they have a technique for doing it. I'm not going to go into it. It doesn't matter. It's impossible. It's incredible. It's unbelievable how they do it. But they do it. They can pull it out. They can disassemble DNA base pair by base pair. It's just simply astounding. And then tell you what you have. Next slide. So, in early 2010, a new geneticist contacted me and offered to help using that new kind of equipment. From 206, the first few of these things that were done, the first few genomes that were recovered were like $10, $15 million each. The price just was plummeting that whole time. So now it's down to maybe, to do ancient DNA, it's just a couple million. Now, a lot of people say, well, wait a minute, why does it cost so much to do the Starchild DNA when I read on the internet that I could, you can have your DNA done for $5,000, $10,000. Well, that's true. You can have your DNA, your genome sequence for about 10 grand right now using this equipment. Because it's fresh DNA. You saw the rubber band pile, all these things do is they unbuckle the rubber bands and just string them out and measure them. Fresh DNA, easy to do. Now, imagine when you're dead for a long time, imagine that wad of rubber bands put through a wood chipper and they're all the little pieces. And that's what you've got to put together to make the genome of something that's been dead for a long time. And that's our problem. To do that, you have to do it again and again and again and again, 50 to 100 times. Run it through the machines 50 to 100 times so that you fill in every gap and you string the rubber bands back together. Basically, yeah. So that's why it costs so much. Next slide. Anyway, when he did, after a few weeks, he recovered and sequenced dozens of fragments of the nuclear DNA. That's all he got the first time. Dozens of fragments, but they were long, but they all came out of the junk. But they were in the hundreds. And so what he did was, when he got those dozens, he sent them all to what's called the NIH database. Next slide. The NIH is the National Institutes of Health in Maryland. And what they have is, in America, they put out the money to most labs to do DNA work. So that if you want to do some kind of work, they will give you the grant money to do it. And in doing so, you owe them the results. And they take the results and they put them in the database. So by the time, by 210, when we were doing this, middle 210, the database was very, very full of literally billions of coherent base pair strings to compare to. All of the human, all the chimp, all the gorilla, and parts of hundreds of other animals. So it had a very, very good spread, down to bacteria and yeast and molds and things like that. Everything anybody did, it went into that database and it was there. So if you had unusual DNA, that's what you did. You sent it there to see if it matched up with anything. Next slide. So what the Starchild did was, some of it did come back in strings that matched up in the human genome. Some of it did. This is one of 265 base pairs. Okay, and it says very clearly that 265 base pairs is found exactly matched in Homo sapiens chromosome 1 genomic contig here. They know where it is, right? But half of the things he sent in, next slide, half of them came back. This is a 342 base pair. No significant similarity found. Not on Earth. So he contacted me and he says, boy, you really got something here. He says, we can have a few of these maybe, but not half of them. He says, you've got something here.